Now that we can calculate mass moments of inertia, we'll use that to solve problems of rotation of rigid bodies. So, start with, let's review our equations of motion. When we take the sum of the forces in the x or the y directions, we're setting them equal to the mass times acceleration. But we have to remember that if a body is rotating or under general plane motion, then the acceleration of different points on the body are going to be different. Therefore, we have to be specific and say that the sum of the forces is equal to mass times the acceleration of the center of mass in the directions that we're looking. In some cases, it'll make sense to use x and y coordinates. In others, we might use normal and tangential components. And in either case, again, remember to take the acceleration of the center of mass. Now, since it's a rigid body, we'll also need a sum of the moments equation. And so we can either sum moments about an axis through the center of mass, set it equal to the mass moment of inertia about that same axis times the angular acceleration alpha. If we take any point in general, then we have to add the other kinetic moments, which are the distance between the point P and the center of mass. Those are x bar and y bar components, times these effective forces, the mass times the acceleration terms that we've talked about when we did translation. But we'll show in class that there is one other alternative where we have a fixed point, and of course we are rotating about a fixed axis, so there will be one point that's fixed. If we take the sum of the moments about an axis through that point, then we can set it equal to the mass moment of inertia through that same axis times alpha. Now, let's look at an example problem. Here's a very simple one where we have a wheel subjected to a moment. And so we might be asked to find the angular velocity or maybe even the angular displacement after a time t once we've applied this moment. So we simply have to use the sum of the moment equations. Sum of the moments about, in this case, the center point is equal to the mass moment of inertia about that same axis through the center point times the angular acceleration alpha. We solve that for alpha and then use our kinematics to find omega. And again, if we were asked for angular displacement, then again, using kinematics to do that. Now here's a problem that's a little bit more involved. It involves a pendulum. And it asks us to find the angular acceleration and the pin forces there at A if we release the pendulum from rest in a position like as is shown here. So for this, let's show both a free body diagram and a kinetic diagram. A free body diagram would show all of the forces acting on the pendulum, which would just be the weight and the pin forces. Now in this case, I've chosen to use normal and tangential components because we know the center of mass is going to create a circular path around the fixed axis at A. So our kinetic diagram, as always, will show the mass moment of inertia about the center of mass times alpha, as well as the mass times accelerations of the center of mass in the two directions, and again they're shown through the center of mass so that when we take the moments we can get the distances correct and the sense correct off of the kinetic diagram. So our equations of motion, let's look at the sum of the moments first. We can do one of two things. We can either take the sum of the moments about the center of mass, set them equal to, again, mass moment of inertia times alpha. But if we do that, that's going to involve the pin forces. A better alternative will be the one on the right. If we take the sum of the moments about an axis through the fixed point, in this case that's going to be point A, then you can see from the free body diagram, all that's going to be on the left side of the equation is going to be the weight, component of weight times the distance away from A. And on the right, as we said, we can set the sum of the moments about a point corresponding to a fixed axis as being the mass moment of inertia about an axis through that point times alpha. So with that, I don't have to involve the pin forces, and we can solve for alpha right away. To find the pin forces, then, we use our sum of the forces. And sum of the forces in the normal direction normally will be mass times the acceleration of the center of mass in that direction. In this case, it's going to be 0, because remember the normal acceleration is going to be r times omega squared. And in this case, because we're dropping it from rest, that means the initial angular velocity is 0. So again, the sum of the forces in the normal direction will be 0 initially. And our other equation will be to take the sum of the forces in the tangential direction. Again, it'll involve a component of weight and the uh, pin force A sub t on the left side, and mass times acceleration of the center of mass in the tangential direction on the right side, so we can solve for the pin forces. Well, next class, of course, the next logical step after looking at rotation about a fixed axis will be to look at general plane motion, where we have both translation and rotation going on at the same time.